sense of continuity. You can hear me and see me as well, right? And also see my slides. If you can confirm, I can go ahead.
Yes, yes, sir. Yes, sir.
All right. So I told you about what are the typical feed to the FCC, what it does, and what kind of products we produce. And we mentioned that it's one of the most important refinery units in the refinery, today, because without fluidized catalytic cracking unit, it's very, very difficult to make the kind of profit margins that we are looking for. And with the current prices of crude oil, the way they are, about $100 per barrel, in fact, this particular technology assumes much, much higher importance. And we went through the brief history of FCC. It's not a very old history. It started only in the last century, early last century, and by the time the World War II took place, this technology actually got well established in order to make gasoline. And we discussed how innovations and research continued, because of which the FCC continued to be relevant to the refining industry, and it continues to be relevant even today because of these developments. Showed you some photographs of the old Dubs cracker. In fact, Dubs process was the very first process which actually started to crack heavier hydrocarbons in our industry, and one of the first patents which actually was commercialized. Then Exxon took the lead to actually come up with the kind of a new generation FCC catalyst that we know today. And what has happened over a period of time? Let me see if I can get my pointer. Um, uh, yeah, the keypad is kind of stuck, so I cannot. I think you can see my arrow, right? So I will use the arrow. So basically, the fluidized catalytic cracking technology as such centers around two major pieces of equipment called the reactor and the regenerator. The reactor actually, by the name, actually cracks these heavier hydrocarbons into light fractions, so all the way from hydrogen to unconverted oil like a fuel oil. And in that process, carbon gets deposited on the catalyst, so it actually goes into the regenerator where the carbon gets burnt off. And the way actually the technology evolved, it went from a fixed bed process like the Dubs cracker to a moving bed and then fluidized bed. And today we have actually riser cracking. And I will get into, in much more depth in each one of them in terms of what is dense bed cracking and riser cracking. In fact, the first unit that was installed in India way back in 1954 by Shell in their refinery here in Chembur in Mumbai was actually a dense bed cracker unit where the catalyst, residence time was like 30 seconds, 30 to 120 seconds. Today, the catalyst is completely fast fluidized in the riser. So the residence time is less than 5 seconds, even in some cases, even 2 seconds. And the vaporization, the vapor residence time is almost half that of the catalyst residence time in this riser. This riser is pretty tall. This could be something like 40 feet for 40 meters tall riser, 30 meters tall, in which actually the feed it takes only 2 to 5 seconds for the hydrocarbons to travel through that long pipe. It's just a hollow pipe, and we maintained temperatures anywhere from 480 to 650, depending upon what severity of cracking we need. And we talked about various feeds and the various products that you produce. One of the major products that we produce is propylene. That is actually in the LPG. That is the C3 component in the LPG is very rich in propylene rather than propane. So we separate out that propylene and then we polymerize that propylene to make polypropylene. And so actually worldwide, the cost of polypropylene production has gone down considerably because of polypropylene being produced from the propylene being manufactured from FCC unit, because FCC unit is handling all these, otherwise low value feedstocks like vacuum gas oil, coker gas oil, deasphalted oil, etc., etc. And we talked about the effect of feed quality on, this is the typical feeds all the way from distillate to hydrotreated distillate, residue, etc., and the typical composition that you get of the product. One of the things which you remember I mentioned very clearly is that there is no mass balance that you can achieve on the FCC. So if you put 100 tons per hour of material in, you will not get 100 tons per hour of products out. You will get less. And that reduction is because of the coke. That means part of the feed actually gets coked up and it gets deposited on the catalyst, and the catalyst actually gets regenerated, so the coke gets burnt off. And that heat that is generated by burning of that coke is actually provided to sustain the endothermicity in the reactor. So basically, the reactor regenerator are completely heat balanced between themselves. So if you look at, if you draw an envelope around the reactor and regenerator, the reactor regenerator system is basically adiabatic in the sense that they don't need any heat from outside. Whatever heat is required to crack the heavier molecules in the reactor, that is provided by burning of the coke in the regenerator. And the heat carrier is the catalyst itself. And we talked about how that is done in this picture. You bring in the regenerated catalyst, which is pretty hot, and then the feed is injected at the bottom, and that actually gets vaporized and cracked and pretty high velocity, all the way from 5 feet per second, 15 feet per second at the bottom to something like 60 feet, 60 feet per second at the top. And that is fast enough to actually take the catalyst along with it, and then it comes out. And here this is the stripper. We'll talk more about the stripper later. The stripper only actually strips any of the entrapped hydrocarbons out, so that they don't go along with the catalyst to the regenerator, because that will be having significant quantity of hydrogen, since it is hydrocarbons. And so actually what we try to do is not to allow any free hydrocarbons going along with the catalyst, and that goes into the regenerator. And in the regenerator, then you have the coke getting burnt off by air, and this heat is actually absorbed by the regenerated catalyst, and that catalyst comes back into the riser. So this is how actually the circle is completed. I also mentioned about the spent catalyst slide valve and the regenerated catalyst slide valve. These are the two valves which actually control the flow of the catalyst from the reactor to the regenerator, and the regenerator to the reactor, correspondingly. And these are very, very important valves, because if suppose these valves fail, then you'll have actually air, because the regenerator is always at a higher pressure than the reactor. So basically, you'll have air then going into the reactor, and at that temperature, it can actually explode. And that explosion will be so great that in a place like Chembur, if you operate such an FCC and there is an explosion there, it can do considerable damage in the thickly populated area of Chembur. And in Chembur itself, if you take into account both BPCL and HPCL, which are right opposite each other on that road going to Trombay, we have 4 such FCC units operating, 2 in BPCL, 2 in HPCL. So it becomes, and this is surrounding all the thickly populated Chembur area. So you can imagine how critical these slide valves are. And similarly, the regenerate catalyst slide valve, which actually separates the regenerator from the riser. And that actually I kind of discussed further in terms of how they control. Actually, the spent catalyst slide valve actually controls the level in the stripper, the catalyst level in the stripper, while the regenerate catalyst slide valve controls the temperature in the reactor. And this is how the controllers are actually configured. And on this diagram, you also see the typical numbers that we use to design these units. Like, for example, the riser residence time is only 3 to 5 seconds. Density of the catalyst is, very, very low. The bulk density is high, but in this case, This is the overall density is only 80 kg per cubic centimeter per meter cube, I think. And then you have temperature at 490 at the top with a very low pressure, 2 kg per. This pressure is also just enough for the gases to go through the main fractionator, etc., which I discussed later. And regenerate temperature at about 690, 700 degrees centigrade, and slightly higher pressure, 2.5. And along with that, we have the connections from both sides. The flue gas. Let me see if I can get my pointer back again. Actually, my mouse somehow is not. Maybe the battery is dead. Anyway, the mouse is not working, so I'll use this pointer. So basically, the flue gas coming out of the regenerator, as I told you, actually goes into a third stage cyclone, where we remove further catalyst, the fines of the catalyst, and then actually it goes into the what we call as a uh, pressure reducing train, where actually it runs a turbine to generate electricity, or actually to run the air blower or the air compressor, which actually runs which goes into the regenerator. On the process side, the process gas coming out of the reactor actually goes into a distillation column, very much similar to the atmospheric column. And we discussed about that as well. So this is what it is. So these gases actually which come out from the top of the reactor, they are pretty hot, as you would imagine, because the temperatures are of the order of 490 and can go up to 550, 560 degrees Celsius. So these gases are very hot the way they come in. And as I told you a long time back, anything above 360 in terms of hydrocarbon can crack and it will deposit coke. So basically, in this case, what we try to do is we take the clarified oil, what we call as CSO, clarified slurry oil, and that is actually cooled in a big cooler, as you can see. And since it is hot at about 360, we actually can generate HP steam in that heat exchanger, which you see at the bottom there. Unfortunately, I cannot get my pointer back today. Otherwise, let me see if if I get any luck. No, I don't think I've been able to get it. Anyway, so here it is actually. So this is the cooler, which actually cools this circulating reflux, because of which we quench the reactor of gases coming in. And then we quench it enough so that only the clarified oil part of the gases condenses, the rest of it goes up. And then we actually separate out the heavy cracked oil. This is called a HCO and LCO, the light cracker oil and the heavy cracker oil. These are actually blended together to ultimately go into the diesel pool. But they are pretty low cetane number or cetane index value number, streams. Then we have actually the gasoline, heavy gasoline, which is separated out. And as you can see, we have the same pump around and the same system that we saw earlier. Whatever cannot condense, along with a pretty large amount of steam, because we got steam used in the reactor, in the stripper and so on and so forth. So there's a large amount of steam which actually goes along with the overhead gases, and the overhead gases are pretty olefinic, because it has ethylene, it has propylene, it has C4 olefins, etc. So they cannot get condensed using cooling water. Otherwise, if you have to condense, you have to go for refrigeration. That will become expensive. So we actually cool whatever it is by cooling water and condense to the extent we can. Obviously, the entire water condenses out, and that actually dissolves all the H2S. So it is called sour water that you see at the top. And you have hydrocarbon. And some of the heavier hydrocarbons will condense, partly, basically, mostly gasoline fraction. And then actually whatever cannot condense goes into what we call as a gas concentration unit. So the liquid from this reflux drum goes to the primary absorber, which I will come to in a minute. And then the uncondensed gases, what we call as the CRAD gases, they go to the gas concentration unit. And in the gas concentration unit, what we do is we take the CRAD gases and we put it through a two-stage compressor. So this is almost like atmospheric pressure, and then we pressurize it to something like 15 bar. At 15 bar, part of the gases do condense, and so we have a cooler, and we part of the gases do condense. Some gases will condense here also. Some of the heavier fractions they condense here, and that is also put along with the effluent from the second stage compressor back into this drum, what we call as. I'm not able to get my pointer here. It disappeared. Yeah, so this is actually called an HP drum, high pressure drum. In our industry, whenever in FCC people call HP drum, it is this drum actually. And what happens is that whatever gets condensed, but a lot of it is still not condensed. Basically, hydrogen C1, C2, to some extent C3, C4. And so they are all in the gas phase here. So that goes into the top column, which you see as primary absorber, where actually we try to condense any LPG components like C3, C4, because C3, C4 components are valuable for us. What is not comparatively valuable is hydrogen, methane, and C2. C2 means ethane and ethylene both. So this is actually taken off it from the top. It is taken off from the top. Yeah, yeah. This is taken out from the top, and we get then go into what is called as a sponge absorber or a secondary absorber, where this liquid is actually coming from this is actually part of the heavy gasoline coming out of the main fractionator. So this heavy gasoline is used to further absorb any of the C3, C4 components which might have escaped from the primary absorber. And then that goes back into the main column. While the liquid which comes down, that actually goes into again the HP drum, and that liquid ultimately finds its way into the stripper. In the stripper, what we do is the reverse of primary absorber. In other words, the liquid which comes into the stripper might contain some of these light gases like hydrogen C1, C2. So we don't want that to come along with the LPG. Otherwise, it will destabilize. It will change the reed vapor pressure of the LPG. So we strip it using reboiled stripper, as you can see from you can see the reboiler at the bottom, and that vapor ultimately joins back again to this stream. So the whole thing is in a kind of a circulation mode till ultimately what you get is the gases, which is hydrogen C1, C2 from the top, and ultimately you get LPG plus gasoline from the bottom, which is actually then sent to something like a naphtha stabilizer or a debutanizer column that you have already read about. Which we covered when we discussed crude distillation unit. And here, this column is operated under high pressure so that we can condense LPG at the top, something like 12 to 13 bar, so that we can use cooling water here. And then the bottom is actually our gasoline, which is the gasoline which we ultimately take into the gasoline blending pool. The experiments that I'm doing right now, because of which I got delayed, is actually our effort in Reliance to ultimately eliminate gasoline production in the future. So what I'm trying to do is actually I'm using this stream from our FCC unit in Jamnagar, the gasoline stream that you see right at the bottom. And I'm trying to actually recover benzene, toluene, xylene from that to aromatics. So that in future we can use this stream as a major feed source to make aromatics, and the rest of the material which is non-aromatic then can go back to the riser to further crack, so that we completely eliminate production of gasoline in the future. We are talking about like 2028, 29 time frame. But for that, actually, the research has to be done now. I might get interrupted in case my experiments get disturbed once more. So this is This is what we call as a gas concentration unit. And the other aspect with respect to this is where actually we stopped last time. So the other aspect with the FCC unit is actually the handling of the catalyst. Okay, and in this case, what we do is, we keep two what we call as bins. Which this is actually the fresh catalyst bin, and this is the spent catalyst bin, or what we call as an equilibrium catalyst. Now, this is in FCC unit. What happens is we actually withdraw the catalyst continuously. And so this catalyst is withdrawn continuously and kept into this bin, while we actually put a fresh catalyst continuously. Now, this doesn't happen like a continuous stream going in or out. What we try to do is that in every shift, we actually withdraw some part of this catalyst and we put fresh catalyst, same quantity. So in an FCC unit, like if, for example, in a typical 1 million ton FCC unit, 1 million ton per annum FCC unit, you would actually kind of replace zero point 0.6 tons per day, zero point 0.6 tons per day. So that is roughly about zero point 0.2 tons per shift. And in an FCC unit like we have in Jamnagar, which is 11 million tons, which we actually change roughly about 20 tons per day of catalyst. So the consumption of catalyst in our FCC unit is like 20 tons per day. In other words, 20 tons of equilibrium catalyst is removed. That is the catalyst which is circulating. What is equilibrium catalyst in our industry? We call it as an ECAT. E for elephant, ECAT, or equilibrium catalyst. The short form is ECAT. This ECAT is actually removed in order to maintain the activity of the catalyst, because in its journey between the reactor and the regenerator, and if you recall, I had mentioned that if you trace one particle of the catalyst in its journey between the reactor and the regenerator, it actually completes the journey in 10 minutes. So every catalyst particle actually travels between the reactor and regenerator in 10 minutes. And so actually in that process, it gets sintered. Also, actually, because of steam, you get hydrothermal deactivation of this catalyst as well. And I do not know whether I have actually shared any information on the catalyst so far with you. I think that might be coming later. We have talked about feed. So, if you recall your feed composition, you see the nickel here in the feed and the vanadium. Now, what happens is that any nickel and vanadium, even if it is at the ppm level, coming along with the feed, that gets deposited on the catalyst. Okay. And later on, I will explain why nickel and vanadium are poisons to this catalyst. What happens is that they, particularly vanadium, it can actually form vanadic acid in the atmosphere in the regenerator, and that vanadic acid can then actually, first of all, it gets oxidized to V2O5, vanadium pentoxide, and then vanadium pentoxide can get further converted to vanadic acid, and vanadic acid can penetrate into the crystalline structure of the zeolite catalyst that we use, and actually completely make the catalyst amorphous. It can destroy the crystalline structure. And that is why actually it is very important to maintain a balance of the nickel and vanadium on the catalyst. I mean, that slide might actually come later. I'll show you a comparison later on between the fresh catalyst and the equilibrium catalyst. So as of now, I think what you have to actually remember is that we take out the catalyst, the circulating catalyst, which we call ECAT, by a certain amount, and exactly the same amount of fresh catalyst we put. There are three very important reasons why we do that. Number one is to maintain the activity of the catalyst, which we call the MAT activity, microactivity test. That is called microactivity test. In short, it is called MAT. So we actually try to maintain that activity in the circulating catalyst. Number two, during this journey, this catalyst also gets attrition. It goes through attrition, so we get a lot of fines made. So we actually withdraw this catalyst to maintain the particle size distribution as well. Otherwise, actually, the flow of the catalyst will get affected. And the third, of course, and the most important reason is actually to maintain the metal balance on the catalyst. Because over a period, within no time, when I say no time means within an hour or so, within a couple of hours, there will be so much of nickel and vanadium which will get deposited on the catalyst that you would actually what you will find is that this nickel and vanadium starts actually converting hydrocarbons. They actually start dehydrogenating the hydrocarbons and produce hydrogen. So basically what we call as dry gas. So basically the dry gas yield goes up. The dry gas is actually the gas coming out of the top of this secondary absorber. This is what we call as a dry gas or acidic gas. And this is useless for us because this is only hydrogen C1, C2. So this is generally put into the fuel gas header of the refinery to be used as a fuel. So we don't want too much quantity of this being made because otherwise it is being made at the expense of some more valuable hydrocarbons like C3, C4 or heavier hydrocarbons. So this is a very important system in the reactor regenerator to remove the catalyst and to be able to add fresh catalyst. And other additives that people add, like for example, CO promoter and so many others. So that also we have separate bins there, which has helped to actually put the catalyst in the regenerator. One thing you have to remember is this catalyst withdrawal and putting back is done from the regenerator and not from the riser, because in the regenerator the regenerator has the largest amount of inventory of the catalyst, and I'll explain later on uh, in what way actually the regenerator holds this catalyst. So this is just a summary of the catalyst regenerator. Pressure vapor phase based cracking. It's not liquid phase. So we vaporize the feed completely, and that vaporization is done based on the hot catalyst coming from the regenerator. So it's a high temperature, low pressure vapor phase cracking. The coke that is produced is unavoidable, and in fact, actually, it is necessary, and it is actually the lifeline, the bloodline of this unit, because this coke, when it burns, it actually generates heat. That is the third line, and that actually heat is required for cracking, for coke combustion. The entire reactor and the regenerator is actually balanced. In fact, the reactor regenerator it is completely balanced in terms of mass balance, heat balance, and pressure balance. And the pressure balance is necessary for control of the unit in terms of moving the catalyst from the regenerator to the riser and from the reactor back to the regenerator. The catalyst is changed during normal operation. So here is a case which is different from the technologies that you have learned so far. Like in isomerization, the catalyst just sits there for maybe 5 or 6 years, and then we shut down the unit and change the catalyst. In the CCR also, in the reformer, the catalyst continues for 5 or 6 years, and then over a period of time, once it gets deteriorated considerably, that is the time to shut down the unit, maintain the unit, and then take it back again with the new catalyst. But here in the FCC unit, the catalyst is continuously withdrawn and fresh catalyst is put in. And this is very different as compared to any other operation that you have learned so far, or you will learn in the future. And so we need to have a continuous inventory of fresh catalyst with us. The hydrocarbons and air are very, very close to each other, so we have to be. So that's why the design of these units is a bit tricky, and a lot of experience is required for designing the standpipe and the slide valves. It is highly flexible unit. It can process almost anything, if you ask me. all the way from C5, C6 hydrocarbons, all the way to short residue. So anything can go as a feed. And these units, by definition, are large. I mean, public sector units have something like 1.8, 2.5. In fact, the largest unit in public sector is in IUC refinery in Odisha. That is around 4 million tons per annum. But of course, SR is higher. And then in Reliance, we have the largest FCC units in the world, of course, and two of them, 11 million tons each. So these units are large. So any small changes or improvements that you make can make a considerable amount of money. Now, as I told you, fluidized catalytic cracking is actually an engineering marvel. And basically, it actually revolves around the theory of fluidization. And this is very, very important for you to learn that fluidized catalytic cracking unit, the science and the technology behind fluidized catalytic cracking is fluidization, which we learned during our undergraduate classes in fluid flow. So what you see on the left is a vessel, let's say, with a grid at the bottom. And suppose if you fill this with a powder, okay, and you start passing air or some gas through it, and you put a delta P measurement across this bed. So you have a vessel in which you put a grid on which you put some kind of a solid bed, which is particles, of course, and you can measure the delta P with the air going through or gas going through. Now, if you plot delta P versus the velocity of the air or the gas going through this bed, what you will find is that initially when the flow is zero, that means the gas flow is zero, there is no delta P, right? Because this delta P indication will show zero. But as you start actually putting air through it, the air actually goes through a pressure drop across this column, across this bed. And that is actually given by Argun equation. If you recall Argun equation from your undergraduate classes, ERGUN, that actually gives you the pressure drop calculation across this bed, which is a function of the viscosity of the gas, the density of the solid, as well as actually the porosity and the density of the gases. So basically, Argun equation will will tell you the delta P, and this is given here. And let me see if I can get my pointer back. Um, yeah, yeah. So basically, this is it will be a linear graph. So as you keep on increasing the velocity, the delta P will keep on increasing linearly till at a point where actually you will start you get a highest delta P and then it goes down. In other words, this bed expands. The more air you or gas you put in, the bed expands. And this is what we call is at the fluidized state. The bed has now become fluidized. And at that point in time, actually, the delta P does go down because of the uh, higher voidage in the system and low overall bulk density of the solid. And then actually that delta P continues to be constant as you actually increase the flow. So this is actually the yeah, the velocity at which you actually get the maxima and then reduce is called as the minimum fluidization velocity, if you remember. So you have a compact bed, which is actually a fixed bed operation, and then you get into the fluidized bed mode, where the bed is in a fluidized bed condition. And then as you actually keep on increasing the flow further and further, that a stage will come where actually this entire powder will just go vanish along with the gases going out, and that actually becomes what is called as a pneumatic transport. In other words, you're using air or gas to pneumatically transport these solid particles into some other location. And that again, then, your Fanning's friction equation that is delta P is equal to 4 FLU square upon 2 GCD. That actually will then tell you what is the delta P, and that's completely a function of Reynolds number at that moment in time. So I again repeat, initially it is a packed bed system, and then which is basically governed by Argun equation, and then you'll start actually seeing an expansion in the bed. I'm sure you must have done these experiments in your undergraduate classes. And then the bed expands, and then that delta P remains constant. And after a certain time, it starts to rise again. And this is actually where the bed will start, getting carried away. The material in the bed will get carried away by the gases going out. Now, this is where actually, the kind of catalyst, the type of material that we use in our SCC unit. I will show you physically the catalyst also in a moment. But let me actually explain what is this catalyst. Now, what you see is actually the characteristics on the left side versus fresh catalyst and our spent catalyst and what we call as an ECAT. So you can see that basically our catalyst is silica aluminate. It is silica alumina, which is basically the composition of sand, on the beach. So that is also silica is aluminate basically. But this is much more purer and much more refined silica alumina. But roughly about 25% alumina, 70% silica. The more silica you put, the more acidity you get actually in the catalyst. And the rare earth is actually to stabilize the catalyst in terms of its skeletal density. You can see there is no nickel and vanadium present in the fresh catalyst. Okay, and these others are basically the binders. Actually, this material is because of the binder that you need to put to give strength to the catalyst particles. And going down further on the fresh catalyst, when you look at the physical characteristic, this is actually the surface area per unit mass, what we call as BT area, meter square per gram, and the elementary cell size, the unit cell size, and the pore volume. The apparent bulk density is around 0.82 gram per centimeter cube. So you can see that it is the apparent bulk density is even lower than water. And this is the particle size distribution. So if you take a mean average particle size, it is roughly around 60 to 80 microns. So it's a very fine particle. The average particle size is around 56 microns. And what you see at the end is the attrition index, what we call as a Davidson attrition index. And we need to have it high so that the catalyst doesn't actually get into a fine powder as it travels between the reactor and the regenerator. But the catalyst which is circulating inside the reactor regenerator, what we call as an ECAT, that data you can see on the right, where actually now you see, very large amount of nickel and vanadium, which gets deposited around 2000 ppm and 3000 ppm nickel and vanadium. Nickel and vanadium put together is about 5000 ppm. So this is something which actually leads to further coking of the catalyst as well as dehydrogenation of the hydrocarbons, and that actually leads to higher dry gas. So we actually try to limit that. So if, in other words, if suppose I'm using a heavier feed, okay, so if I'm taking short residue, obviously in short residue, the nickel and vanadium is high, and all of that will get deposited on the catalyst, right? So particularly if I'm using a heavier feed in my feed to the FCC unit, my catalyst change out will be much higher. In other words, my catalyst requirement will go up. I'll put more fresh catalyst and withdraw more e-catalyst. And actually, you can do this calculation on a piece of paper. So if I'm putting, let's say, a feed containing 10, not 10 ppm is too high, but something like 2 ppm of nickel along with the feed. And I'm putting something like 100 tons per hour of feed. So 100 tons into 1 ppm of nickel, you can calculate how much of tons of nickel is going in. And if my catalyst to oil ratio is about 8, that means for every ton of catalyst, every ton of feed I'm putting in, I'm circulating 8 tons of catalyst. That means that much tons of nickel will get deposited on the catalyst. So if suppose I have 1 ppm of catalyst coming in, that catalyst will ultimately get deposited on the catalyst. That nickel will ultimately get deposited on the catalyst, and it will keep on building up because there is no escape. Okay, so it will keep on building up. So you can calculate like in one day how much nickel I have put in the feed along with the feed. So ultimately, how much would be the nickel ppm level in the catalyst? And there's a certain limit beyond which we don't go. Those numbers, that is what you see here, about 2000 ppm, 3000 ppm. Even these numbers are a bit high. And we actually try to stabilize the concentration of nickel and vanadium below these numbers by putting more and more fresh catalyst. Now you can see that the surface area goes down because of the centering of the catalyst. So so we need to replenish this with the fresh catalyst. And also actually you get more and more attrition, so your average particle size can in this case actually the particles got agglomerated here because of hydrothermal deactivation of the catalyst in the regenerator. So all of that is actually stabilized by putting more fresh catalyst and removing ECAT. In fact, this is the best time for me to show you. I brought it to my office today in the morning from home because I knew that I'm going to give this lecture from office today. I do not know whether you can see, but if you can see, just let me know. So I'm just holding it in front of the camera and I'm just trying to pour this catalyst. Can you see the catalyst getting poured? I'm pouring it into the container at the bottom. Are you able to see?
Yes, sir.
Yes.
Yeah, so I'll just hold it in my hand and show you. So it is like powder like this. You see how easily it is slipping through my fingers. So this is actually the white powder that you see. This is actually not the fresh catalyst. It is actually equilibrium catalyst. If you see closely, which you cannot see sitting there from that so long distance, actually this catalyst is not very white. It is slightly black, and because of the coke deposited on the catalyst. I'll just show you again. Are you able to see? So it's almost like a liquid. You can pour it. You see this? I can literally pour it like this. This is the catalyst, which is the bloodline of the FCC unit. This is actually does all the magic in terms of cracking the heavier hydrocarbons to whatever lower hydrocarbons we produce. And in fact, you will not be able to see it, but I can see some small carbon particles in this catalyst actually. I don't think you will be able to see it from that distance. But let me see if I can bring a bit closer. Are you able to see the catalyst in this container? I'm bringing it very close to the camera.
Yes, sir.
Yeah. Yes, sir.
So I'll bring it very close to the camera and show you. Do you want to see more, or you've seen it enough, right? So this is the catalyst that I was talking about last time, and since we are talking about fresh catalyst and ECAT, I thought this is the right time to show you. Just a moment. The catalyst got onto my keypad. Okay, it's a very fine powder. It actually by by doing that, it got all over my office here. All right. Okay. Now, we talked about this fluoridization in the bed and the various regimes we talked about. Now, as far as FCC is concerned, in fact, not FCC, if you talk about any fluoridization, this is actually what happens in this bed. So, in this particular section, which I was telling you, so this is the fluoridization section, right? And as you keep on increasing the gas flow, what happens is that it actually goes through various regimes of fluoridization. So this is your delta P versus the flow chart. This is what is the fixed bed, right? This is actually the Argun equation part of the fixed bed. So you can see that the bed is of constant height. Now, as I increase the velocity further and it goes through the minimum fluidization velocity, the bed expands. And that, overall bed density goes down. The what you call the voidage goes up. And because of that, you get a fall in delta P. But the bed expands, but you can still see a very clear surface on the top of the bed. As you go up on velocity further, you see bubbles of gases actually. Actually, physically, you can see the bubbles of the gases going through. Here, you cannot see the bubble, just the bed expands. But if you go further, you get bubbles going through. This is called as a bubbling regime. As you increase the velocity further in this range, then you actually get into what is called as a slug flow regime where the bubble sizes go up. In fact, these bubbles, they coalesce together and they form larger bubbles. And these bubbles actually expand the bed further. Okay. And the bed is still very, very clear at the top. And then when you go up further on this, then actually you get into a turbulent regime where the bed height remains the same, but now the clear shape of the bubbles disappear. You see large gas, columns actually shooting around the bed. And then once you go beyond that, in fact, once you are actually in this region, then you get completely pneumatic conveying of the bed. In fact, the riser of the FCC unit operates in this regime. And I'll show you each one of these regimes here. Let me show you here. Then we'll go back to the previous slide because it's having understood this, that let me actually go through this once more. Fixed bed, then expanded bed, then you have a bubbling bed, then you have a slug flow regime, and then the turbulent regime, and then fast fluidization, or what we call as pneumatic conveying. So if you look at each of the sections of the FCC unit, let us start with the riser. Okay, this is where the feed enters, and we have the injectors and the hot catalyst coming in, vaporizing the feed and cracking the feed. This entire pipe, what we call as the riser reactor, is actually in the fast fluidization mode or pneumatic transport mode. As I said, something like 5 to 20 meters per second or 5 to 60 feet per second. So 5 at the bottom, 20 at the top. And that velocity is good enough for fluidizing that catalyst. You know, that catalyst which I just showed you just now. It's a very fine powder. And this actually, if you are not able to touch this catalyst, but if you hold it in your finger, it doesn't actually, like for example, जैसे हमारे घर में talcum powder होता है, so if you actually put talcum powder on your hand, it sticks on your hand. You have to actually wipe it from with a piece of cloth if you want to get your hands completely free of talcum powder. This is not like talcum powder. This is actually spherical. These particles are spherical, very tiny particles, 60 to 80 micron type. So actually, when I was taking in my hand and I was pouring it like this, it did not stick to my fingers. I can show you again. Of course, it will, So let me see. Let me show you again. So so I'm taking the catalyst. and I'm pouring it into this container, right? And if you see my finger, they're slightly colored, but if I just you can see that it is all gone. So it's a very spherical powder, you can see. And this actually helps, it gets fluidized much easier. And this particular powder is actually in a complete fast fluidization mode in this part of the section of the reactor regenerator. Once it comes out, then it actually fills up this stripper, and we put steam here. Now, this stripper is also actually fluidized. The catalyst is fluidized here, but it is in the bubbling regime. Bubbling regime means in this regime. It is actually operating in this regime. And then once it actually goes into the standpipe, the standpipe is actually minimum fluidization. So this is like your expanded bed. This is it is in this regime, the standpipe. And of course, we put steam, what we call as a fluidization steam, across the length of this standpipe, so that actually the what you call the catalyst remains in the fluidized mode. And then you have a catalyst getting into the regenerator. In just a moment. Yeah, what? चालू हो गया foaming. Okay. Just give me 2 minutes. I'll just come. Okay, so this is actually coming into the regenerator, and the regenerator is in the turbulent bed mode, zero point 0.7 to 1 meters per second. You see this? This is the turbulent bed mode, and from after the regenerator, again it goes into the standpipe, which is actually at the minimum fluidization value. So you can see that the SCC unit operates in all the regimes of fluidization, all the way from pneumatic transport to the bubbling bed to the turbulent bed. Okay, and of course, the standpipe, which is actually in the minimum fluidization mode. This slide actually summarizes what we discussed so far. How do I get rid of this? Um, okay. So this is the fluoridation regimes in these. So between right up to minimum fluoridation velocity, the bed is fixed. The particles are quiet. There is no the gas flows are through the interstices. Between the fixed bed and the minimum fluidization, the bed expands, as I said, a smoothly in homogeneous manner. The top surface is well defined, a small scale particle motion. And this is the region when flowing catalyst angle of internal friction about 70 to the horizontal. So this is actually the kind of motion that you see in the standpipe. Now, between the particulate regime and the bubbling regime, actually that this is actually the bubbling regime in the stripper. So the gas voids form near the distributor, coalesce and grow, rise to the surface. So this is good enough. So the steam actually it is the steam bubbles in the stripper which actually help to strip out the hydrocarbons, and they actually are small bubbles which go bubble through the bed. So that is why it is called the bubbling regime. We don't operate in the slug flow regime, but directly in the regenerator, which is the turbulent regime. So small gas voids and particle clusters dart to and fro, and top surface is difficult to distinguish. Okay, and then we come into the fast fluidization mode, where there is no upper surface of the bed. The entire particles is actually carried away by the incoming gases. So this is and ultimately pneumatic transport. So this is all the three types of fluidizations that we see in SCC unit. All the four: the fast fluidization, the bubbling fluidization, the minimum fluidization, and the turbulent bed in the regenerator. So this summarizes the kind of velocities and the bed densities we maintain. Like in the standpipe, it is 700 to 800 bulk density kg per meter cube. In the bubbling bed, that is in the stripper, it goes down, and that's how the hydrocarbon gets stripped out. In the turbulent bed, which is actually the regenerator, the air which we put from the bottom, that burns off the carbon, and you actually get CO and CO2 formed. And that actually helps to, and this large expanded bed of regenerator helps to capture the heat and brings it down. So this is a summary of the fluidization